Hi, thanks for joining us for this second video in Chapter 9, the reactions of alcohol. Last time we talked about Fischer esterification and how that same mechanism applies to the chromate ester formation mechanism as well. And today we're going to kind of do something similar, sulfonate ester formation, which sulfonate looks like, or I should say sulfonate ester looks like this as an example, where I want you to notice how this part looks like an carbon-based ester, right? Like alcohol portion of it and then the carbonyl portion of it. So that's an example of a sulfonate ester. The most common very common reagent is this toluene sulfonyl chloride. Maybe I'll add that here. Oops. The short for it is toxic chloride. Toxic chloride. It's abbreviated like this, and often it's accompanied by pyridine, which has the structure that looks like, that's a pyridine. It's basically a benzene ring with one of the atoms replaced with nitrogen, one of the carbons replaced with nitrogen. Okay, now so of course this alcohol can be converted to this tosylate, which often is abbreviated kind of like this. That's the same thing. Okay. It's a condensation reaction with alcohol. It's a condensation of this sulfonyl chloride with alcohol. And of course these reactions, or I should say these functional groups, sulfonates, are very useful as excellent leaving groups, as you might remember from chapters 6 and 7. Here's the mechanism. Hopefully it looks very familiar, right? Now this functional group is very electrophilic because you got a sulfur that's tetrally 4 times bonded to oxygen, and also chlorine, which are all very electron withdrawing electronegative atoms, right? So for that reason, this is a very electrophilic atom. Because it's so electrophilic, even a weak nucleophile like alcohol can actually attack it. Okay. Now, if you add another bond to sulfur, even sulfur cannot have more than 6 bonds, even though it accommodates more than octet because it's a third row element with access to the d orbitals. You have to kick a pair of electrons up and now I'll let you in on a secret. The benzene ring, instead of drawing the 3 double bonds, you could abbreviate it like this. That means the same thing. That's a benzene ring. Now, once we get to this intermediate, right, we have pyridine, which is mild base. It's a decent base. It's not a good base, strong base at all, but that can pull off that extra proton, okay, and that's why they're there to facilitate that process. Another way I can sort of abbreviate that benzene and a methyl group here, which is called toluene. I could just say that's the aromatic group. So this stands for aromatic. Maybe I should write that so you don't think that's argon. Okay. Now, the next thing that happens is just like with Fischer esterification, this very crowded structure gets collapsed by kicking off a leaving group, which chloride is a great leaving group. So that can leave. And in the end, you'll have the sulfonate ester product. And of course, you have a chloride leaving group as well. Now, all that to say, tosyl group is, or tosyl chloride is very useful in turning alcohol into a great leaving group. And that's going to be really important when we think about synthesis of compounds, right? As a synthetic chemist, you might want a particular alcohol to be a good leaving group, but alcohol is not a good leaving group. What can we do? We could make it into a tosylate sulfonate group, right? So we've already seen how sulfonates are useful in SN2, E2, SN1, and E1 reactions. And of course, I'll just refer you to chapters 6 and 7 notes. But it's also useful for reduction of alcohols to alkanes, as we'll see here. Okay, so here's an example. Let's say you have this alcohol that you want to turn into propane, the alkane. I mean, that's kind of an expensive way to make alkane, but one of the things you could do that is you could make it into sulfonate. And the second thing we've already encountered, that's short for pyridine, but this top thing, that's not like some master's degree in chemistry, but this is mesylate is the short. Oops. Or I should say mesyl chloride, which will make mesylate. It looks exactly like this, toluene sulfonyl chloride, except instead of toluene you just have a methyl group there. Now that will get us to this group, which again is the same as that's short for that. There's that methyl group. And once you make a sulfonate, you could treat this, which by the way this is called a mesylate. You could treat this with lithium aluminum hydride, which is a very strong source of hydride. If you recall, a good solvent for that would be ether. And you could replace that oxygen with hydrogen, which, you know, this is the same thing as just propane, the alkane. Excuse me. Now, you might be wondering, could we have done this with tosylate? Yes, of course. You could have used tosyl chloride or tosyl chloride here instead. I just used mesylate or mesyl chloride as for variety. Okay. Now, how does the mechanism go? Mechanism is pretty simple. Here's aluminum hydride, right? And here's the mesylate, or the sulfonate. Remember, this is an excellent leaving group, and this is a good source of hydride, not proton, hydride with a negative charge. With 2 electrons can attack here in an SN2 form fashion, and that's how that would happen. Okay, Now, another very similar situation is you could turn, if you need alcohol to be a good leaving group, you could turn them into halogens, haloalkanes from alcohols. One way we could do that is through what we just did. So let's say you want to turn this into a halogen. One of the things you could do, you could tosylate it, right? Through the sulfonate, and then you could treat this with a good nucleophile halide like iodide, say in acetone. The iodide would do SN2, and you could get an halogen or a haloalkane from the tosylate like this. So that's one way to do it. Another way might be, right, you could use a hydrohalic acid. So those are like HCl, HBr, HI. Those are hydrohalic acid, hydrogen on a halide acid, right? You can't quite do this with HF or hydrofluoric acid. And that's a super toxic and dangerous material, so you probably shouldn't use it anyway. And then another catch is you have to, it needs to be a primary or secondary alcohol. Okay. So in this example, you would end up with this primary bromide. How does the mechanism go? Well, remember that hydrogen bromide is a strong acid. Strong acids do the same thing in organic chemistry that they did in general chemistry. They just simply protonate, right? Or donate proton. So it does to the lone pair. Which would make that oxygen a good leaving group. And then you have a bromide left over, right, which is a good nucleophile. So it could do SN2, like this. Right, and then I think we talked about an example like this back in chapter 6, I believe. So hopefully this is just a review for you. Another example, right? You could treat this with hydroiodic acid, and that would end up with inversion, of course, right? The catch or caveat is these things could with SN1 mechanism through the carbocation like this. So that means you get a little bit of the other enantiomer, just a little, because some of the molecules go through this carbocation, which of course can give racemic. Right, most of it is going to go through SN2, but there's a competition there that you have to be aware of. Another method is to turn it into turn alcohol into a chloride using thionyl chloride, which is this reagent. It's called thionyl chloride, SOCl2. Now, this is kind of interesting because you could do this with retention of stereochemistry. Which tells you that the mechanism is not an SN2 mechanism. Okay, so how does that work? Well, As you can imagine, like before, the sulfur is very electrophilic because it's doubly bonded to oxygen and also doubly bonded to chlorine, which are all very electronegative. And so even a weak nucleophile could attack it because it's very partially positive. Like so, which by the way, this sulfur does have, interestingly, a lone pair on it. This is your nucleophilic addition step, if we want to name it. And it looks intermediate, of course, would look like that. Which, by the way, can you tell what hybridization this sulfur is? With 4 things attached to it and a lone pair. So this is sp3d hybridization, and the molecular geometry is seesaw, if you remember the Vesper table. Now, when this collapses, right, to kick off the chloride, it's just in the right vicinity of this positively charged oxygen or alcohol to do this intramolecular frontside attack. The orientation of this chlorine on this thionyl chloride is just so that it doesn't, you cannot reach the back side of it because it's kind of too far. But it attacks from sort of the same side as the alcohol in the thionyl chloride. Now this reaction technically is called SNI. I for nucleophilic substitution internal, and the end product is the retention. So that's the mechanism there. Now, the last of this kind, another reagent often used to turn alcohol into a halide is phosphorus tribromide or phosphorus trihalide. And this, once again, goes through SN2, as you can tell by looking at the product structure. Inversion always implies SN2. Now, to understand this mechanism, you kind of need to know, to be let in on the secret about sort of the gossips of who likes who among the periodic table classroom, and that's that the phosphorus really loves oxygen. They have like a crush on each other. Okay, that's a really helpful thing for you to know as a chemist. If phosphorus can have oxygen all to themselves and vice versa, they would. That's a really helpful thing to know in organic chemistry. Now, not surprisingly, oxygen would like to attack phosphorus, partly because this phosphorus is partially positively charged with electronegative things attached to it. So bromide is a good leaving group, so this is basically an SN2 reaction that happens. Now, what that does is this whole thing really is a good leaving group. And then we just spit it out a bromide ion that can act as a nucleophile. So this can do an SN2. right? And you end up with that bromide. And the byproduct, of course, looks like this. Now, this still has 2 other bromide on it, so this can still keep going on reacting. Indeed, if you have another alcohol like that, this could do another round of reaction. In fact, 2 other rounds of reaction, until the phosphorus ends up only surrounded with oxygen. And that's kind of the love story that erupts up between phosphorus and oxygen. So that's kind of the driving force, but phosphorus dibromide is a good reagent for this. So now you have some tools to convert alcohol into a good leaving group. That's kind of the message today.